Let's solve a couple of linear homogeneous recurrent sequences following the models we discussed in class. So let's take the first example. Xn equals 2, xn minus 1 plus 12xn minus 2. There's the recurrence relation. And then with the initial conditions, x0 and x1 equals 2. So let's see, x0 is x0 is 7 and x1 is minus 5. So let's, given this piece of information, this is the recurrence relation, which is linear, homogeneous, constant coefficients of order 2. Order 2 because every term in a sequence is a linear combination of the two previous terms. And these are the initial conditions, ICs. And this is the recurrence relation. Okay. Our task is to provide an explicit formula for the sequence. Okay, so step 1. Let's write down the characteristic equation. First of all, it's important to know when you write down the characteristic equation what's the order of the recurrence. So we have an order 2 that we discussed before. The order is the how many terms prior to xn we need in order to calculate xn. So the past goes back up to xn minus 2. So 2 steps in the past. So the order of the sequence is 2. Then if the order is 2, xn will be substituted by r squared. Xn minus 1 will be substituted with r to the power 1, which is r, and xn minus 2 will be replaced by r to the power 0, which is 1. So the characteristic equation will be r squared equals to r plus 12, or r squared minus r minus 12 equals to 0. Okay, so let's write down the outcome of step 1. Characteristic equation is r squared minus r minus 12 equals to 0. Step 2. Now that we got the characteristic equation, we have to solve it. So solving the characteristic equation amounts to characteristic roots. Characteristic roots. Characteristic roots, we either apply the quadratic formula for an equation of degree 2 or we factor. In this case, it's quite easy to factor. Is r minus 4 times r plus 3 equals to 0. So that's r squared minus r minus 12 in a factor form. So the characteristic roots are r1 equals to 4 and r2 equals to minus 3. And this moment is an important moment, it's kind of a fork in the road. If the characteristic roots are distinct, we do something in the next step. If the characteristic roots are repeated, we do different things. So in this case, the characteristic roots are distinct. And the fact the characteristic roots are distinct has consequences in how we write down step 3. So given the characteristic roots are distinct, it leads us to the following step 3. With distinct characteristic roots. Distinct characteristic roots. So based on the fact that the characteristic roots are distinct, the expected or projected form of the sequence. So expected plus projected form of the sequence is xn is a linear combination of the n powers of the characteristic roots. So it's c1 as 4 to the power n plus C2 times minus 3 to the power n. So we expect the sequence to be of this form. The only thing we don't know are is the constant C1 and C2. So, okay. So step 4. In step 4, we find the constant C1 and C2. Let's see which piece of information from the problem we didn't use yet. This is the initial conditions. So in step 4, we use the initial conditions. Which are these ones, x0 equals to 7, x1 equals to minus 5, to find C1 and C2. Okay, how to use those conditions? Well, if we set n equals to 0, and we can do this and use the fact that x0 equals to 7. So if we set n equals to 0 in this formula, we get C1 plus C2 equals to x0, which is 7. Then, if we set n equals to 1, so set n equals to 0 here. If we set n equals to 1, in the formula, expected form of the sequence, we get 4C1 minus 3C2 equals to x1, right? x1 will be minus 5. And what we got here, we got a system of linear equations. In one way or another, solve the system. Let's do it by elimination. So multiply the first equation by minus 4 and add the second equation. What do we get in this way? C1 will cancel. We'll get here minus 4C2 minus 3C2 minus 7C2 equals to minus 28 minus 5 minus 33. So that implies that C2 equals to 33 over 7. Then C1, we can find C1 by using C1 plus C2 equals to 7. So by using C1 plus C2 equals to 7, C1 will be 7 minus C2. It will be 7 minus 33 over 7. So C1 equals to 49 minus 33 is 16 over 7. So we got C1 and C2. Okay, so we got everything we need. So we are ready to formulate a conclusion. So in step 3, let me summarize what we got in step 3. Use the initial conditions to find C1 and C2. And we got C1 equals to 33 over 7. And C2 equals to, no, C2 equals to 33 over 7. And C1 will be 16 over 7. So let's formulate the conclusion. That means the explicit formula for the sequence. Step 5, explicit formula for xn. The explicit formula for the linear homogeneous constant coefficients recurrent sequence is xn equals C1, which was 16 over 7 times 4 to the power n, plus 33 over 7 times minus 3 to the power n. So this will be the explicit formula for this sequence. Okay, so now let's discuss a different problem in that at the moment of the fork in the road moment, we have to go ahead with repeated characteristic groups. So let's see what we do that. Okay, so The second problem is the following. The sequence is, the recurrence relation is xn equals to 4xn minus 1 minus 4xn minus 2. Then x0 equals to 13 and x1 equals to minus 5. Okay, so again, let's do the steps we indicated in class. So step 1, characteristic equation of the sequence, given that the order is 2, is r squared equals to 4r minus 4, or r squared minus 4r plus 4 equals to 0. So that's the characteristic equation. Step 2, the characteristic roots, which are obtained by solving the characteristic equation. How to solve it? We just factor it. So that would be r minus 2 squared equals to 0. This one is a double root. So this implies r1 equals to r2 equals to 2. So we are in the case, again, we are at the fork in the road moment. So look at the characteristic roots. In this case, we notice that they are equal. So we are in the case of repeating roots. So this brings us to step number 3. Expected slash projected form. Given that we have repeated characteristic roots, or double roots, when xn equals to c1 times to the power n, we cannot say plus c2 times to the power n for obvious reason, because it's nothing different. So exactly like people do in differential equations, repeated roots are modeled by using extra powers of x for differential equations and powers of n for sequences. So plus c2 times n times to the power n. So that's the expected formula sequence for a double root 2 and 2. And there's a very general idea. So hypothetically, let's spend a couple of seconds to discuss what about if a root will be 2, 2, and 2. So it's a triple root. So it repeats 3 times. So what would be in that case hypothetically? Xn will be, in this case, c1 times to the power n plus c2 times n times to the power n. So that stands for the first repetition, plus c3 times n squared times to the power n, because again every subsequent repetition of 2 amounts to an extra n used in this in the next step. Right? If it repeats one more time, I have another plus c4 n cubed times to the power n. Okay, let's get back to the main course. So this will be the expected formula sequence in the case of a double root 2 and 2 repeated. Step 4, like always, so far we didn't use the initial conditions. Use the initial conditions to find the constants C1 and C2. Okay, so how to do it? So in this case of a double root, it's even easier, because if we set n equals to 0, this term will essentially disappear. So if we set n equals to 0, what do we get? This formula becomes C1, and that's it. C1 equals to x0 is 13. If we set n equals to 1, what do we get? 2c1 plus 2c2, just setting n equals to 1 here, 2c1 plus c2 times 1 times to the power 1, 2c1 plus 2c2 equals to x1 equals to minus 5. So we got c1 equals to 13. We got c1 on a plate, so this is it for c1. And now 2c1 will be 26. And 26 plus 2c2 equals to 5, minus 5. So this implies c2 equals to, go 26 from left to right, because minus 26 minus 5 is minus 31. So minus 31 over 2 is c2. So we just use the initial conditions to find C1 and C2. Here they are. C1 equals 13, C2 equals to minus 31 over 2. Okay. Step 5. The conclusion. The conclusion. The explicit form for the sequence is xn equals to 13, which is C1, times 2 to the power n, minus 31 over 2 times n times 2 to the power n. We can, okay, if we really want not to use denominators, so for xn equals to 13 times 2 to the power n minus 31 n times 2 to the power n minus 1. Sometimes you may want to give a common factor to the exponential function to write the right hand side here as a product between an exponential and a linear term. If we have to. Okay, so that's the second problem. The third problem will involve a very classical sequence, namely the Fibonacci sequence. And let's find one of the most celebrated formulas in discrete mathematics, Binet formula for the Fibonacci sequence. Okay, so this is the problem. F n equals to Fn minus 1 plus Fn minus 2 for every n greater than or equal to 2. That's the recurrence relation for the Fibonacci sequence. And F0 equals to 0 and F1 equals to 1. So that's the presentation of the linear homogeneous constant coefficients recurrent sequence known as the Fibonacci sequence. And if you want to look at the first few terms, 0, 1, 1, then 2, 3, 5, 8, 13, 21, 34, 55, 89, 144, and so on. Then we have a terms of the sequence. We notice a certain exponential growth. So how exactly is exponential growth with basis remains to be seen. So let's see. So step 1. So let's find an explicit formula for the Fibonacci sequence. Characteristic equation is r squared, because the order of the sequence is 2, Fn will be r squared. So f r squared equals to r plus 1, or r squared minus r minus 1 equals to 0. In a previous problem, we just, to solve the characteristic equation, we just factor. Now, in step 2, find the characteristic rules by simply use the quadratic formula. Right? So R1, comma 2 equals 2. So for the quadratic formula, A equals to 1, B equals to minus 1, C equals to minus 1. So, what's the quadratic formula? Minus B plus minus square root of B squared minus 4AC over 2A, which is, in this case, 1 plus minus square root of 1 minus 4 times A times 4 times 1 times minus 1. So 1 plus 4, it will be 5. So 1 plus minus square root of 5 over 2. 1 plus square root 5 over 2 and 1 minus square root 5 over 2. Distinct. So again, for distinct roots, we go to step 3. The projected form is Fn is C1 times 1 plus square root of 5 over 2 to the power n plus C2 times 21 minus square root of 5 over 2 to the power n. Okay, this will be the expected form of the sequence, of the Fibonacci sequence. Step 4. Use the initial conditions, f0 equals to 0, f1 equals to 1, IC is initial conditions. Use initial conditions to solve for C1 and C2. We do it exactly as we always do. So set n equals to 0. If we set n equals to 0, what do we get? C1 times 1 plus root 5 to the power 0, that's a 1. So C1 plus C2 equals to F0, which will be 0. So C1 plus C2 equals to 0. And then let's set n equals to 1. What do we get? C1 times 1 plus square root 5 over 2 plus C2 times quantity 1 minus square root of 5 over 2 equals to, if n equals to 1, equals to F1, which is 1. And again, this is a system. How to solve this system? Well, the common sense way will lead us to solving for C2 in terms of C1. C2 equals to minus C1. So keep this in mind and replace it in here. So the second equation, where we replace C2 with minus C1, becomes C1 times 1 plus square root of 5 over 2 minus C1 times 1 minus square root of 5 over 2 equals to 1. Or if we give a common factor, C1 times, open a bracket, 1 plus square root 5 over 2, a fraction, minus another fraction, 1 minus square root of 5 over 2 equals to 1. So let's see, inside this bracket, 1 over 2 minus 1 over 2, they simplify. And what's left? We are left with a square root 5 over 2 minus square root 5 over 2 plus another square root 5 over 2. So square root 5 over 2 plus square root 5 over 2 eventually is square root of 5. So inside this bracket is actually square root of 5. So what we got here? C1 equals to 1 over square root of 5 and C2 equals to minus C1 minus 1 over square root of 5. Okay, so we are done with step number 4. Let's erase the work and keep the truth. So C1 equals to 1 over square root of 5, C2 equals to minus 1 over square root of 5. And step 5, the conclusion. Fn equals to 1 over square root of 5, which is C1, 1 over square root of 5 times 1 plus square root of 5 over 2 to the power n minus 1 over square root of 5 times 1 minus square root of 5 over 2 to the power n. Or if you want to give a common factor of 1 over square root of 5, we get a celebrated Binet formula. Fn equals to 1 over square root 5 times, open a bracket, 1 plus square root of 5 over 2 to the power n minus 1 minus square root 5 over 2 to the power n. So this will be Binet formula. Binet's formula. So this is an explicit form for the Fibonacci sequence. Now let's come back to the exponential growth and see what is actually the basis for this exponential growth. Let's erase those things. Give the Binet formula. So again, we put again here, Fn equals to 1 over square root of 5 times 1 plus square root 5 over 2 to the power n minus 1 minus root of 5 over 2 to the power n. Right. So, okay, let's see, what's square root of 5? Square root of 5 is basically 2.23, give or take. So this one is 1 minus 2.23, so this would be a number minus 1.6, give or take, over 2, minus 0.618 to the power n. A number being minus 1 and 0 to the power n approaches 0 when n goes to infinity. So when n is large, the nth Fibonacci number can be approximated with 1 over square root of 5 times simply 1 plus square root 5 over 2 to the power n. And this number, this is basically an exponential growth. And this number is the golden section. 1 plus 5 over 2 equals to the golden section. Or ratio.